So the next talk is revisiting collision and local opening analysis of ABR hash by Chandranan Dhar, Yevgeniy Dodis, Mridul, Nandi, and I think one of the authors should share the screen. Is it Yevgeniy or who's giving the talk?
Definitely not me. I hope it's Chandran, but I mean, I'm okay. I really hope one of.
Wonderful. Yeah, Chandran is here.
Okay,
Yes,
thanks.
I'll just share my screen.
Please go ahead. Yes.
Okay.
Yep. Yeah,
So,
looking forward.
so hi, I am Chandranan Dhar, and I am going to give a short talk on revisiting collision and local opening analysis of ABR hash. This is a joint work with Yevgeniy Dodis of New York University and Mridul Nandi of Indian Statistical Institute. So, in Eurocrypt 2021, Andriva Bhattacharya and Roy defined a tree-based hash construction, which they call the augmented binary tree or the ABR mode in short. So basically, this is a construction that is based on the Merkle tree hash, but in addition to the message blocks that are there in the leaf nodes, what they do is they XOR one block of message at each non-leaf node, and also we have some feed forwards. So this constant, so the diagram we have is that of an of ABR3, that is the ABR tree of height 3, but the same thing happens for a general tree. So this the ABR tree is an interesting construction. Why? So first of all, we can see that it is 50% more efficient as compared to the Merkle tree. So this is because of all this message that we are introducing in the non-leaf nodes. But also, if the ABR construction is found to be collision resistant, then you can see that this matches the much coveted Stamps bound, which is an open problem for a general construction since Crypto 2008. So what Stamps construction does is it for a compressing primitive, it relates the R, that is the number of calls to the compression functions, and T, that is the number of blocks that can be computed using this R compression functions. So for a 2n to n bit compression function, so what the Stamps bound states is that R should be greater than or equal to 2t minus 1 over 3. So if we look at the ABR tree, so this matches the Stamps bound, that is R equals 2t minus 1 by 3. So if the ABR construction is found to be collision resistant, then we are basically solving an open problem. But is it collision resistant? That we are going to see soon. So first, let us have a look at the claims on the ABR hash. So the authors of ABR, they claim some things which we revisit in our work. So first of all, they assume that first they say that assuming the underlying primitives to be independent random oracles, they show that the ABR mode is collision resistant up to the birthday bound. So they also have some results regarding the pre-image resistant and indifferentiability, but we don't look into them in our paper. So further, so what they do is they propose a very efficient local opening of ABR-L, that is the ABR mode of the general height L. So to prove the membership of a message block, it is required to open 2L minus 1 blocks, and then it is required to make L compression function calls to verify. As an example, let us look at a specific local opening of the ABR of height 3, that is ABR3. So in this tree, so to prove the membership of the first message block, that is M11, we need to open 5 blocks, which I have depicted in blue, and then to verify the membership, so we require the 3 compression function calls, F11, F21, and F31. So this specific local opening for a general tree ABR-L was suggested by the authors of ABR in their paper. So our first result actually shows that the local opening that's suggested by the authors of ABR is not secure. In fact, we show that there exists a collision attack on the local opening with at most 2 to the n over 2l queries. And then we try to generalize. And we show that there does not exist any non-trivial local opening of ABR that achieves birthday bound security. So these are results regarding the local opening of the ABR hash. But then we move on to the main proof in the ABR paper, that is the proof of the collision resistance. So first we have a look at how they try to prove the collision resistance of ABR hash. So first of all, their proof of the collision security can be divided into two main parts. First, they define something called the load and bound the load. And then they bound the collision probability in terms of the load. So what is the load? The load on a node is defined as the total number of computable messages in the subtree of the node. So the load can also be seen as the total number of hash outputs generated at the node. So if the node is a root node, then this is the final number of hash outputs that we get. And if the node is an intermediate non-leaf node, then basically we are looking at the number of intermediate hash outputs at that node. Why are these two the same? This is because each computable message will lead to a hash computation at that node, and unless a collision occurs, so each computable message leads to a distinct hash computation, and so these are basically the same. So now we look at several mistakes in the collision analysis proof of the authors of ABR. So the first step is of course bounding the load of the ABR tree. So the first mistake that they do while bounding the load is that one thing we see first is if we allow at most row multi-collisions at any node, then each of these row queries at the node j minus 1, 2b can potentially give at most row multi-collisions again at the node jb. So inductively we can see that at any node at depth j should have row to the j multi-collisions at that node. But the authors of ABR just say that we can allow row multi-collisions at each node, and they just miss the power j. So this is a minor fixable issue, and it does not degrade the bound too much, I believe. But the next mistake that they do again while bounding the load is not fixable, what we think. So the thing is, the bounding the total number of newly generated hash functions at a node V is very easy when the final query is at that node itself. And it is also relatively easy when the final query is at a child of V. But when the final query is further away in the subtree of V, so bounding the number of newly generated hash functions is not very easy. So I don't think why, but the authors of ABR, they do not discuss this, and they just claim the result using an inductive argument which we could not verify. So as an example, so in this diagram, so let us say we want to bound the load at the node V, and the final query with the final query response pair is x1 concat x2 comma y at a grandchild of V. So we can see that if we want to bound the number of newly generated hash functions, that is the load at V due to this query, so our result will depend on a lot of extra terms that I am marking in blue. So this is not very easy to bound. So so we have written an expression for this in our paper, but we don't have a proper bound for this. So these mistakes were there while bounding the load, but in the next step, that is bounding the collision probability in terms of load, they again mess up. So like what they say is the collision probability at the root node is basically load square over 2 to the n. But they don't explain anything. Like they don't support their claim. They don't say what happens. They just say that as analyzed for ABR2, this holds. But ABR2 is a very basic construction, and we don't see why this should hold for ABR of any height. In fact, by showing a counter example, we show that this statement is not true in general. So in particular, we construct a hash mode based on a 2-to-1 compression function where the load is around q square. However, a collision can be found in order n queries and not q to the 4 by 2 to the n, which should be load square by 2 to the n. So again, there is a mistake. But the mistakes do not end here. So we then find that the authors of ABR have missed one collision case altogether. Like, how can the ith query at a node V lead to a collision? So one case can be that the one output among the newly generated hashed outputs due to the ith query can match with one of the previously generated outputs by the I-1 queries, and then we can have a collision. So this is what we call the non-twin collision, and the authors of ABR discuss only this type of collision. However, we also have another type of collision, like the ith query at the node V generates more than one final hash values. So two among them can match, and so in the among the outputs of the ith query itself, we can have a match, and this will lead to a collision. So we call this a twin collision because this has occurred from the ith query itself. So the authors of ABR completely missed this, and we also find that bounding the analysis of such a collision is non-obvious, and it requires us to bound some additional bad events, and it is not easy. So what we see is that the proof that there are many mistakes in the proof of the original proof given by the ABR authors, and we find this pretty unfixable. So we again try to prove the collision security from scratch, and we basically show that a correct collision analysis requires us to bound 5 random variables. These are size of the multi-collision set at a node V for some query xi, then the load at the root of the tree, and then load at the subtree of the root, subtree rooted at the node V where the final query comes, and then two other things called the size of the cross collision and the size of the delta collision, which I am just going to discuss now. So first, so what is a cross collision? So a cross collision arises from the analysis of a non-twin collision. So again, see if I say again, so how does a non-twin collision occur? It occurs when my ith query at a node V, when the ith query at the node V leads to a hash output which matches with the previous hash output that is generated by the I-1 queries, and then thus we have a collision. But then just immediately before the ith query, what we have is that there must be some full message M, that is a message for the full ABR tree, and a partial message M prime. There is a partial tree starting at the node V, which gives us a collision. And what happens at the ith query is we find, so one of the hash outputs matches one of the hash outputs at the node V. So the size of the cross collision is the number of such message pairs M prime, where M is a full message and M prime is a partial message starting at the node V. So if we have a bound for the cross collision, and if we can bound the load at the node V, then we can bound the cross collision probability. So that is what we show in our paper. And then the delta collision arises in the twin collision case. So what happens in a twin collision case is that for both the trees, the query at the node V is x1 concat x2 and the response is y, and this leads to a collision. So first we see that if this is the case, then the difference between the message that is there in the V, that the node V, that the difference between MV and M prime V is the same as the difference of their outputs. That is MV XOR M prime V. If this equals delta, then what we have is H1 XOR H2 is also delta. So if we fix some delta, so for a twin collision to occur, so what we must have just immediately before the ith query at the node V is there are two partial trees. One starts at the output H1 at the node V, and one starts at the output H2 at the node V. Their XOR is delta, and for two messages M and M, two partial messages basically M and M prime, there is a collision. So this is what we call a delta collision. So delta collision means the size of the delta collision is basically the number of such message pairs M and M prime, both of which are partial messages starting at the node V and which further satisfy that H1 XOR H2 should be equal to delta. So what we actually show in our paper is that if we can have a bound for these 5 random variables, we essentially have a bound for both the twin collision and the non-twin collision, and hence we can do a proper collision analysis. But for a general ABR tree of height L, we find that giving a correct proper bound for all these 5 random variables is a bit difficult, and so the collision analysis is incomplete. But what we have managed to show is that for the first non-trivial case, that is the ABR tree of height 3, it is actually collision resistant up to birthday bound. That is the dominating power here is n to the 5 q square by 2 over n. So by 2 to the n. So this is asymptotically this collision resistant up to the birthday bound. And since I seem to have some time, so let me quickly go through why this collision analysis of ABR3 cannot be extended to the collision analysis of a general ABR tree of height L. So first and foremost, so there is a simplification that is available for the collision analysis of ABR of height L for any arbitrary height L. So what we can do is the adversary can first make all the queries to the leaf nodes, and then they can move to the lower levels. So this we can do without any loss of generality, because the query response pair that we have from querying at the leaf node is independent from the rest of the transcript. Like the queries at the leaf nodes do not depend on anything else. So even an adaptive adversary can make a query to the leaf nodes first and then move to the lower levels. So how does this help in the analysis of ABR3 but not in the analysis of the greater lengths? So the thing is, as we have told first, so first thing to note here is that, so if we do this, then the final query that leads to a collision happens in either the root node or a child of the root node. But as we have said earlier, bounding the load is relatively easier when the final query happens at the root node or a child of the root node. So the grandchilds we already query first, so that the final query cannot happen in any of the grandchildren. So bounding the load is relatively easy, and then the analysis is not very difficult. But for a ABR of height greater than 3, so the grandchild is not the leaf node. So the final query can happen at the grandchild, and then giving a proper bound to the load is not easy. Also, we have seen that bounding the non-twin collision is relatively easier compared to giving a bound to the twin collision. So what happens for any ABRL is a twin collision cannot occur because of a query at the root node. Because if a twin collision has to occur due to a query at the root node, then we have the same Y for both the queries, and for a collision here, the feed forward needs to be the same. And if the feed forward needs to be the same, then we already have a collision for this subtree, and actually we are actually giving a bound to the proper collision, like when we are giving a collision analysis of ABRL, we assume that ABRL minus 1, that is any subtree of ABRL, is collision resistant. So actually, so in the construction of ABR3, so what we have is, if there is a twin collision, the final query can happen at either in F1 or F2. So there is only two possibilities, and even we have to use a brute force, we can show it for two places, but it does not, it is not easy when there are more levels. So, I mean, this is more or less what we do in our paper. So again, to conclude the things, so first we show that ABR hash cannot have any non-trivial local opening which achieves birthday bound security. And then we identify some serious gaps in the collision security proof. And then finally we show that the first non-trivial case, the ABR3, achieves birthday bound security. So thank you for your attention, and I am open to any questions.
Thank you, Chandranan. Any questions from the Zoom audience or from the people in the room? So I have a question myself. So for L bigger than 3, the ABR construction is not collision resistant, or it's not collision resistant for the birthday bound, or we just don't know?
No, it is, we just don't know, because I mean, so what we can show, I mean, what has already been shown in a different setting by Menning and Prenil in 2016 is that, I'll just go to the first ABR3 for, so if the queries happen layer wise, that is, if we first query at the leaf level, and then this level, and then this level, then this is collision resistant up to the birthday bound. So I mean, this is what in a non-compressing setting, Menning and Prenil, for a somewhat similar construction, they have shown in 2016. So a similar thing goes through in the case of ABR as well. But intuitively, so if the queries are done layer wise, then you can have much more information. Like if you have done all the queries at F1, F11 and F12, then you can much more, I mean, intuitively it looks like at F21 you can make better queries. So, I mean, if it is in an, I mean, not layer wise setting, so it should still follow the birthday bound security, but the proof, I mean, is very hard. Even in the Menning Prenil, their setting, they could also prove it in, I think, q cube by 2 power n, and not q square by 2 power n.
So for
while,
so for bigger than 3, it's still plausible that it is. We just don't know the proof yet.
yes.
And
we conjecture it is. It like lies on stem bound. It's yeah. Unfortunately, it's like those things are like too many cases in the current proof technique. They kind of grow. If you look at our terms, there is like n to the 5. The previous ITC we had a paper about effect something equivalent to ABR2. I think it had a term n squared times q squared. So this kind of trajectory, even if it succeeds, it has like more and more cases. It seems like this n power will become like something like n to the l, which will be kind of meaningless for l, like logarithmic or something. I mean, it's like super complicated. We don't know how to do it, and it looks like it has this terms like n to the L. So it appears we need to find something where there is like a fixed, like I don't know, n square and cube thing which doesn't grow with the depths. And we tried hard. I mean, the reason we looked at this thing was like, how come they have such a short proof, and we like struggled so much last year even for ABR2. We had some
Yes.
preliminary results for ABR3. We wasn't sure it was publishing, so that's why we started to look at that paper. It's like, oh my god, there are all these gaps. So, but yeah, it's like looks hard.
And you mentioned there is a construction from 2016 in which if the queries are layer by layer, you can actually prove that to be secure as well. So is
Yes.
that construction also candidate construction to be collision resistant, or up to birthday bound, we don't know, or we clearly know that that construction is not a good candidate for the general case?
I
I
mean,
think Chandranan can answer. Yeah, go ahead. Yeah.
so I mean, they also have a conjecture that it should have birthday bound security, but they were also unable to prove it for non-layer.
Yeah, most
That's
likely
an
it's also
area.
it's very similar. It's like it's slightly different setting parameters. It's like length preserving, but it's basically it's almost equivalent, just tiny changes. So if this is secure, then the other one is, I'm sure, secure as well.
Got it. Thank you.
Okay, I'll just stop my screen share.
There is no other questions. I thank the Chandranan one more time and the authors of the paper.